Hello guys. In this video, I'm gonna explore with you another connection in electric circuit, which is the parallel connection. Parallel connection. So in the last video, we explored or we studied the series connection. This is the second most important connection in electric circuit, which is the parallel connection. You must understand both very well, very well. Otherwise, you will not be able to analyze circuits. You know. So the condition, for parallel is much simpler than, series. Basically, here for two elements or more to be in parallel, they must have the same terminals. As simple as that, same terminals. Okay. So, for example, a resistor has two terminals. So let's, for example, have a two resistance like this, one like that, R1, and another one like that, R2. And look again, geometry, new geometry. You can draw whatever you like. For these two resistance, which looks like far apart, to be in parallel, they must have the same terminals. So let's assume this is terminal 1, V1, for example, and this is terminal 2, V2. This is, for example, V3, and this is V4. So to be parallel, they must have the same terminal. So basically, the terminals should be connected to each other. So if I connect V1 to V2 and V3, to V3 and V2 to V4, this is parallel. Yes, R1 now is parallel to R2, and this is how we write parallel. When you analyze a circuit. Okay, same example. I'm gonna do another connection. R1, R2. I'm trying to copy, but anyways, this is V1 again, V2, V3, and V4. What if I did like that? V2 and with V3 and V1 with V4. Look, guys, this is a bridge. This is called bridge. That means this short doesn't, touch this short. They are over each other. They are not connected. They are over each other. Is this parallel? Yes, it's parallel. Because they have the same terminals. One of the terminals of R2, which is V3, is connected to V2. The other terminal of R2, which is V4, is connected to the other terminal of R1, which is V1. And by the way, you can do this in another way. You can take R1 and flip it. So I'm gonna flip R1. So basically, V2 will be here and V1 will be here. R2 still the same, V3 and V4. And let's connect what was connected. V2 is connected to V3. And the V1 is connected to V4. They are just exactly the same, equivalent. And both are parallel connections. R1 parallel with R2. Okay? And I want to say here that regardless of the geometry, just to check the terminals. If the terminals are connected, first terminal here is connected to the first terminal here, second terminal here is connected to the second terminal here, you have a parallel connection. And this can be like for two elements like this, or maybe more. So that's a parallel connection. R1 is parallel to R2. Why? The first terminal, or the top terminal, for example, of R1, this node here, let's call it V or V1, is the same as the second, the top terminal of R2. The bottom terminal of R1, which is this here, is basically the same as the bottom terminal of R2. Let's call it V2. Again, all of this is just one node. This is a short circuit. We elongate it, we draw it like a wire, but it's just a node. And again, if we change the rectangle, shape into a curve like that, still the same. So this is also same point. The bottom point or the bottom terminal of R1 and R2 are the same, and the top terminal of R1 and R2 are exactly the same. Still R1 is parallel to R2. That's equivalent. And you can just, make them horizontal. It's fine, Again, geometry doesn't count for us. What counts for us is the connection. So again, the right terminal of R1 or left terminal of R1 and R2 are the same, and the right terminals of R1 and R2 are also the same. For example, V1 and V2. V1, V2. Make one straight line, the other is curvy, doesn't matter. It's still the same. This is V1, this is V2. This is same node. This is same node. They are parallel, and that's equivalent. And still this is equivalent, although it is so like fuzzy, It's still R1 parallel to R2. It's the same terminal. All of that is just one node. And all of that is just one node. V1, V2. Okay? Good. So what is the properties of two or more parallel resistors or elements, whatever? They have the same voltage. That's the most important. They have the same voltage. Let's explore why. Okay? When I say, let's go down a little bit. When I say, so same voltage. When I say I have a resistor like that, R1, and they have two terminals, V1 and V2. And I have a resistor, another resistor, let's call it R2, and they have two terminals, V3 and V4. And V1 is connected to V2, and V2 is connected to V3, and V2 is connected to V4. So they are parallel. Because now V1 and V3 are the same. Let's call it V and V dash, for example. And V2 and V4 are connected to each other, so just one point. So that's V double dash. So if I want VR1, and let's put the direction of VR1 like that. As we will explain in the future, a voltage across the resistor, can have a direction like that, and the head of the arrow is actually the positive terminal, and the bottom of the arrow, the tail of the arrow, is the negative terminal, and that's VR2. Head is positive, tail is negative. So VR1 is equal to the positive minus the negative. So it's equal to V2 or V double dash now minus V dash. And VR2 is equal to the positive minus the negative. Positive is V4, but it's now again we connected V2 to V4, so they become one terminal, which is V double dash. And V3 is equal to V1, and both of them we called them V dash. And look, guys, that's exactly that one. VR1 equal to VR2. Is this true for more? Yes, of course. Let's have another example. Or let me put another resistor here. R3 between V5. Sorry, this is V5. And V6. And we connect V1, V3, V5 together. And we connect V2, V4, V6 together. That's VR2. And that's VR3. VR3, again, V double dash minus V dash. So again, that's equal to VR3. If you have even infinite number of parallel resistors, they must have the same voltage. And one common situation is that you're gonna find in many circuits something like that. If you have like a resistor like that and a battery, these guys are connected in parallel, as you see, because this is one point. That the right or the left, the right terminal of the battery is exactly the right terminal of the resistor. The left terminal of the resistor is exactly the left terminal of the battery. The battery has a voltage E, and we're gonna explain in the future that the battery has a voltage like that, a direction of the voltage like that, because the positive terminal, the long terminal is the positive, the short terminal is the negative. So VR is like that. Let's call this one V positive. Let's call this one V negative. So VE is equal to V positive minus V negative. VR is equal to again V positive minus V negative. Oh man, they are exactly the same, correct? So that means VR is equal to E. You're gonna see this many times, many times. Good. Finally, what is the equivalent resistance? So if I have two or more resistances connected in parallel, can I remove them and just put one resistance? Yes. So what is the value of this? It's C, R equivalent. We learned that R equivalent for series is basically R1 plus R2 plus R3 until Rn. Here, it is not directly like that. You can't directly calculate R equivalent. You can calculate its reciprocal, and then you flip that again and find the resistance. So for two resistances, first case, two resistances, R1, R2, between VA and VB, you can actually remove R1 and R2 and put R equivalent. Look now at the law. This is the law here. 1 over R equivalent equal to 1 over R1 plus 1 over or divided by R2. So it's not directly you can calculate R equivalent. Once you find 1 over R equivalent, you can flip that again and find R equivalent. And just a special case, if R1 equal to R2, in that case here, 1 over R equivalent is equal to 2 over R. And in that case, R equivalent is equal to R over 2. Oh, it is less than R, correct? Because it's half R. So it's less than R. So as we're gonna see in 1 minute, in series connection, R equivalent is higher than or the maximum between the resistances. It's always larger than the maximum resistance, and actually larger than all of them combined. In here it will be less than the minimum resistance, but just 1 minute. Okay. The second case, what if we have n resistances? Number 2, n resistances. R1, R2, R3, Rn between VA and VB. We can draw that in that way. This is R equivalent. This is VA. This is VB. So in that case here, 1 over R equivalent is equal to 1 over R1 plus 1 over R2 plus 1 over R3 until you reach 1 over Rn. Special case, if R1 equal to R2 equal to R3 equal to Rn equal to R, So in that case, 1 over R equivalent equal to N over R. And from that, R equivalent is equal to R over N. So we always divide, right? We always divide. So a common rule here, R equivalent is always less than the minimum of the resistances that are connected in parallel. So number 3, rule R equivalent is less than the minimum between R1, R2, Rn. For example, let's take an example. If R1 is equal to, for like 3 resistances, for example, R1 is equal to 1, R2 equal to 2, R3 equal to 3. So R equivalent must be less than 1, which is the minimum. This is the minimum between 1, 2, 3. Just calculate it. You're going to find it less than 1. Okay? I'm going to leave this to you. So that's basically it. That's basically the parallel connections. Okay? So in parallel connection, we don't care about the geometry, just like series. And just like all electric circuits, we just care about the connections. They must, for 2 resistances or 2 elements, whatever they are, to be connected in parallel, they must have the same terminals. Okay? You can draw, these like connection in any way. That doesn't change the fact that they are in parallel. If you have like 2 or more elements that are connected in parallel, they must have the same voltage. And finally, for the equivalent resistance, it is not directly calculated, but you can calculate it. R equivalent is equal to 1 over R equivalent is equal to 1 over R1 plus 1 over R2 until 1 over Rn, whatever the number of resistances that you have. One last point here before I conclude. If you have 2 resistances, you can write this in this way. R equivalent equal to R1 multiplied by R2 divided by R1 plus R2. That's just, a special case if you have like 2 resistances. And finally, R equivalent must be less than the minimum between the resistances that are connected in parallel. Okay, guys, thank you very much for watching and see you in another video. Bye-bye.